Yeah, okay. And this is, okay. Okay, thank you very much to the organizer for having me here today, and good afternoon, everyone. So today I'm gonna discuss about diffusive shock acceleration at wind shocks in AGN-driven outflows. So this is the outline of my talk. So I will introduce what are ultra-fast outflows that are actually a possible realization of this AGN-driven winds. Then I will discuss and I will sketch our model for particle acceleration and transports in these winds. And I will finally show you our solution in terms of accelerated particle spectra and finally discuss their multi-messenger implications. Okay, so let's get started. As you might all know, the accretion activity of supermassive black hole can have several feedback. The most famous is highly collimated and relativistic jet, for instance, like in Blazar. But another very common feedback is large opening angle outflow that is actually observed in the majority of active galactic nuclei. And ultra-fast outflows are a possible realization of these large wide-angle outflows. So they are inferred to be localized on relatively small scales, namely from a fraction to 10 parsec from the central engine. And thanks to X-ray iron line measurements, they are inferred to be as fast as a sizable fraction of the speed of light, from few percent to few tens percent. And they are indeed, as I already said, inferred to be with having a wide opening angle. And finally, their mass loss rate is inferred to span over several orders of magnitude, but typical values are from fraction to tens of solar masses per year. Okay, so how do we model these outflows? So first of all, we need to understand the structure and evolution of this kind of winds. And if you imagine that supermassive black hole at the time t0 starts its accretion activity, and due to some process that might be MHD driven or radiation pressure driven, a wind is launched, the wind starts expanding in the surrounding medium, and this wind is with high velocity and it's supersonic. Therefore, it drives a forward shock in the external medium, and the impact of this wind outflow with the external medium is responsible for the formation of an inner shock known as wind termination shock. Okay, so, and sorry, let me go back. As soon as the wind sweep up an enough amount of matter, with enough, I mean a matter amount comparable with the total mass in the wind starts its deceleration phase, like in the supernova remnant case, the set of Taylor phase. Okay, so the structure is the following. We have a non-ion-like structure with a fast, cool wind that is impacting with the wind termination shock with a high Mach number. Then we have the wind termination shock heating up and shocking the plasma. And here we have the hot shocked wind. And the contact discontinuity is the boundary of the wind that is separating the hot shocked wind from the shocked ambient medium. And finally, the forward shock is bound in the system, and the actual Mach number of the forward shock depends on the temperature of the external medium. So it's somehow model dependence on the environment where this wind is expanding. So, but the guarantee, the discontinuity that we believe is a guaranteed accelerator is the wind termination shock, where we know due to the adiabatic cooling in a spherically symmetric system, we know that this wind is going to come really fast and with high Mach number at the wind shock. So we model particle acceleration at this wind termination shock. So in the deceleration phase, as I said, we have two shocks that are expanding with this self-similar power laws in time. So both shocks are actually expanding, and the wind termination shock, which is actually a reverse shock, differently from the supernova remnant case, is sustained by the outflow and keeps expanding, but it decelerates faster than the forward shock. Therefore, in time, the shocked wind region expands while remaining adiabatic, and here we have, since the wind termination shock decelerates pretty fast, we have basically that the relative speed between the plasma and the shock is equal to the velocity of the plasma in the rest frame of the source. So we want to model the transport equation in this environment. Since we know that these outflows are believed to be with a wide opening angle, we assume spherically symmetric outflows. And by looking at the typical timescale we expect from this system, we know that we can actually see here that a stationary assumption can be performed. Here you can see the timescales versus energy, and here is the acceleration timescale that together with the escaping through advection, diffusion, and energy losses, they are shorter than the black line here, which is the age of, that we took, for instance, of 1,000 years. And since all timescales are smaller than the age, we perform a stationary assumption. Therefore, we can drop the time variation term in the transport equation. Okay, and for the magnetic field, it's highly unknown, and we assume as a rule of thumb that the magnetic field energy density is taking a fraction, epsilon b, of the order of few percent of the run pressure in the fluid. And we estimate the diffusion coefficient adopting the quasi-linear theory, where, as you can see here in this formula, where delta we assume 3.5, namely we put ourselves not in the bound limit, but in what we expect to be the turbulence in the MHD case, namely a Krasnian-like turbulence. Okay, so as a boundary condition for this problem, we assume spherical symmetry, namely a null net flux at the center of the system, and we take the forward shock not as a possible region where we can have reacceleration. This is a huge complication of the model that might be a possible follow-up, but we consider it just as a free escape boundary point. Okay, so this is how the transport equation looks like in full glory with in the spherically symmetric assumption, and we solve it assuming that the diffusive shock acceleration is just taking place at the wind termination shock, as I said. Then we follow the transport of the particles in full glory, taking into account advection, diffusion, and adiabatic energy losses and gain. And we take, as I said, the forward shock as a free escape boundary, so we also can compute the escaping flux from this ultra-fast outflow, namely what these outflows are injecting in the galaxy, because they are relatively small. And we take into account catastrophic energy losses such as PP or P gamma interaction through photomeson or Bethe-Heitler interaction on the big blue bump, the X-ray, and the torus radiation field of the associated to the accretion disk. Okay, so what about the solution? So we assumed this set of parameters just for the benchmark case I'm going to show you. And we solve the transport equation with the in an old-fashioned way, namely the technique that was already discussed by Blanford in the 80s. We integrate the transport equation in the upstream to get the upstream solution. We get the solution in the downstream in the similar way, and we integrate across the shock, assuming continuity. Clearly, the equation is way more complicated than the infinite planar shock, so we develop a code to solve with an iteration technique this transport equation, but the physics is pretty straightforward, and from this couple of equations we can get the main physics of our solution. So here I'm showing the solution in momentum space multiplied times e to the power second, and here the solution in physical space, where R is the radius. So here we get basically a power law with a double exponential cutoff where gamma 1 comes from the upstream region and gamma 2 from the downstream region. And at low energy, as we might expect, since we are studying diffusive shock acceleration, we get this E2 minus 2 spectrum for the accelerated particles. And interestingly, we get maximum energy for this kind of sources of the order of the 10 to the 18 electron volts. So we arrive really into the energy range of ultra high energies. And this maximum energy is actually regulated by both by advection escape, but also by the far infrared field produced by the torus in this environment. So it's a combination of escape and energy losses that determines this maximum energy. Okay, so what about the solution in physical space? So here is the upstream. This vertical line is the position of the wind termination shock, namely where particles are accelerated. And here you can see with moving from the red to the blue and the black, namely increasing energy, that high energy particles are homogenized in the upstream region, while low energy particles are compressed to the shock. And this is due to the competition between diffusion that try to homogenize particles and advection that pushes particle back to the shock. While in the downstream region, we get that when for low energy particles where advection is dominated, the spatial distribution is flat, while when at higher energy, when the diffusion is dominated, okay, we get softer spectra. And when we explore the spatial distribution as a function of the radius in the downstream region, we can see the role played by diffusion, advection, and adiabatic energy losses. In particular, the spectrum steepens, as you can see here. And when we compute the escape influx from these sources, what we get, interestingly, is that this competition between diffusion and advection produces this dip due to the P-gamma interaction on the big blue bump of the emission of the disk. That is basically this region here in energy, which if we want to fit it with the power law with exponential cutoff, we get that basically in the last decade of our energy range, the spectrum behaves like an E2 minus 1 multiplied times the super exponential cutoff E over E max to the power second. Okay, so moving on, very last slide on multi-messenger implications. So from that spectra, we compute PP and P-gamma interaction in the environment. Here I'm showing with the thick lines the gamma rays, and with dotted lines the associated neutrinos coming from the shocked ambient medium layer in blue, from the shocked wind region in pink, and via PP, and via P-gamma, we get this neutrino flux while the gamma ray is really absorbed. So this is, as you can see, already starting from a few tenths GeV, we get a very relevant gamma-gamma absorption, and this is due to the big blue bump field, while the torus is absorbing then everything at higher energies. And looking at neutrinos in the TV band, we get that we can observe in this energy range. We see that the source is partially opaque to gamma rays with a suppression of 2 orders of magnitude or so, while the neutrino comes with a flat spectrum. And at higher energy, we get a prediction for this kind of sources with a relatively flat neutrino flux in the energy range from 100 to TV to 100 PV. Okay, and this leads to my final take-home messages. So DSA can take place efficiently at wind shocks of UFOs, and maximum energy as large as some EeV can be achieved. And if we take into account this interplay between escape and energy losses, we can get hard spectra injected in the galaxy, and this might be interesting for Auger, for the Auger community in terms of the result of the combined fit, I believe. And possibly UFOs can be bright neutrino sources while being partially opaque in the TV range and totally opaque in the PV. So, and